Hi everyone, today we are exploring a mathematical tool that turns what looks like an algebraic nightmare into a simple trigonometric notation. This is the De Moivre's theorem, the ultimate code for complex numbers. Before we get into the math, I want to set 3 clear goals for our next 10 minutes. First, we are going to define exactly what De Moivre's theorem is. Essentially, it's the bridge between trigonometry and algebra. Second, we'll learn how to apply it. I'll show how to take a complex number to a high power, like the 10th or 100th, without filling up 5 pages of scratch paper. And finally, we'll identify why this matters. This isn't just math for the sake of math. It's a tool used every day in fields like electrical engineering and digital signal processing. But before we look at the formula, we have to look at how it was discovered. De Moivre's theorem is named after Abraham de Moivre, a French mathematician born in 1667. Due to religious persecution, he moved to England where he continued his mathematical work. And in 1707, de Moivre discovered a pattern connecting complex numbers and trigonometric functions, especially when raising complex numbers to higher powers. This discovery later became known as de Moivre's theorem. Although de Moivre introduced the idea, it was later refined and made more popular by Leonhard Euler, who introduced Euler's formula. This formula shows a deep connection between exponential functions, trigonometry, and complex numbers. And today, de Moivre's theorem plays an important role in mathematics, physics, and engineering. Here's an interesting fact. De Moivre was so obsessed with math that he actually calculated the exact day of his own death. He noticed he was sleeping 15 minutes longer every night and used a simple math sequence to predict the day he'd never wake. And he was right. It shows that to De Moivre, the world wasn't just random. It was a series of patterns and sequences waiting to be solved. Now back to the math. To understand his theorem, we have to stop looking at complex numbers as coordinates on a grid like a plus bi and start looking at them as vectors with a length r and an angle theta. This is called polar form. By using the radius r and the angle theta, we turn complex numbers into something that looks like a rotating hand clock. Once a number is in this form, raising it to a power becomes much easier than doing standard algebra. This shift is what allowed de Moivre to find his famous connection. And to define de Moivre's theorem, we look at what happens when we raise a complex number to a power. Usually, in algebra, powers are difficult. They involve multiplying. It's basically just 3 steps to complete the calculation. So let us dive into some detailed calculations. First, we need to move from the rectangular world to the polar world. Plot 1, 1 on the complex plane. Using the Pythagorean theorem, the distance from the center of R is the square root of 2. Since the x and y values are equal, angle theta is exactly 45 degrees. And now we apply de Moivre's magic. We take that square root 2 and raise it to 10th power, which gives us 32. Then we take our 45-degree angle and simply multiply it by the exponent 10. That gives us 45. That gives us 450 degrees. And Finally, we simplify. A 450-degree rotation is just a full circle plus an extra 90 degrees. If you look at our complex plane, 90 degrees points straight up at the imaginary axis, and the cosine of 90 degrees is 0. The sine is 1. So our final answer is 32 times I. No long-form multiplication, no binomial expansion, just a few simple steps of rotation and scaling. This theorem isn't just work for powers, it works for roots too. And if you look for the fifth root of a number, they aren't just random points. Because they are equally spaced by the theorem, they form perfect geometric shapes. The roots of a complex number form regular polygons, triangles, squares, and pentagons, hidden right there on the complex plane. This symmetry is vital in fields like electrical engineering and signal processing. Now you might wondering, when will I ever use this in real life? The truth is, you're using it every time you check your phone. In electrical engineering, we don't just use standard numbers for electricity, we use complex numbers called phases. When engineers design the power grid of the circuit in your laptop, they use the Moivre'S theorem to calculate how waves of electricity shift and rotate. Without this math, our modern power system would be incredibly inefficient. In signal processing, this theorem is the backbone of how we handle data. Every time you listen to a digital music file or use noise-cancelling headphones, a computer is using the Moivre'S theorem logic to break down complex sound waves into simple rotations. It's also how we compress images into JPEGs files so they don't take up too much space. And finally, in the world of quantum physics, the tiny particles that make up our universe don't move in straight lines. They behave like waves. Scientists use these complex rotations to predict where an electron might be. And from the massive power lines outside to the smallest atoms in your body, the Moivre'S works in is the math that describes how the world oscillates and spins. To wrap things up, let's look back at what we've covered in the last 10 minutes. We defined the theorem, moving from the standard rectangular view of numbers to a polar view that lets us rotate through the complex plane. And we applied the formula to turn a messy algebraic expansion into a simple multiplication, and we saw how those answers form perfect, symmetrically polygons. And finally, we identified its legacy from Abraham de Moivre's obsession with patterns in 70s London to the wave analysis used in your smartphones today. And the Moivre's once said that math is an art of finding patterns, and I hope today you've seen the beauty in those patterns. And that's all. Thank you for your time.